Now that we've taken a look at the idea of continuity, limits, graphs, and domain of functions in two variables, we're going to start taking a look at one of the most substantial portions of the course where we start talking about partial derivatives. A partial derivative is essentially going to be a derivative of a function with respect to a specific variable. And what it does is it enables us to be able to find the slope of the function in that direction at a specific point. So we could find the slope in the x direction, the slope in the y direction. We remember from Calculus 1 that we had these limit definitions. And there are limit definitions in Calculus 3. And here they are, just to illustrate what they look like. Not saying that we are going to use the definition of the partial derivative, but if you wanted to, you could just say x plus h comma y minus f of xy divided by h. And remember in Calculus 1, remember it was f at x plus h minus f at x divided by h. So all we're doing is we're just throwing in that second coordinate y to be able to use the limit definition. Now that's the partial derivative with respect to x. Partial derivative with respect to y, we're going to do the same thing except make it y plus h. Again, we could use the definition of derivative, however, we're not going to. Just to make sure we all understand the different notations, all of the following mean the partial of the function f with respect to x. So whenever you see f sub x, that means you're taking the partial with respect to x. Whenever you see this notation, partial of f with respect to x, it means the same thing. In fact, it kind of means the derivative of f with respect to x, except that we use this symbol. It's like a curly, almost like a 2 or something like that, to denote partial derivative. Right? If you ever see this notation f1, all right, that means you're taking the derivative with respect to x. This is your differential operator. Okay, so for the most part, we're going to be using f sub x and df dx. All right, although we may see a few of the other ones along the way. All right, and the same thing that we can use for f, or the same rules for f of y, excuse me. Except that what we're going to do is we're just going to change all the x's to y's, and we're going to take the partial derivatives with respect to y's using these notations. All right, so how do you find a partial derivative? So it's actually fairly easy. All you're going to do is you're just going to, if you're finding f sub x, just pretend that y is like a 5 or a pi or whatever it is. In other words, it's just a constant, and it just stays there. And you're just going to find the derivative with respect to x. Same thing with f sub y. To find the derivative of f with respect to y, all you do is you just take and hold x constant. If you need to take a second or third or fourth partial, then as you can imagine, you're just going to repeat the x. So fxx, fyy. All right. Even a second partial could be fxy and fyx. All right. So those are most likely the notations we're going to use. We're going to be using this notation as well. So the second derivative of f with respect to y squared. Right? Or if you're doing x then y or y then x, then you're just going to have the order in the denominator, partial y, partial x, partial x, partial y. All right, so that's just a brief overview of the notations, limit definition, etc. Now let's take a look at several examples where we are just going to find the partial derivatives. All right, so let's start off with a really basic polynomial function, and we want to find f sub x. So easy enough. Our derivative of x to the fifth, 5x to the fourth. Very easy. All right. Derivative of 3x squared y cubed. Now what I'm going to do is I'm just going to drop down the y cubed because it's a constant, and then the derivative of 3x squared is just going to be 6x. So notice that the y cubed just came on down as it was like a 5 or a pi. The derivative of y to the fourth, now think of that as like a 5 to the fourth, and the derivative of 5 to the fourth is 0 because it's a constant. All right, so the derivative of y to the fourth with respect to x is going to be 0 in this case. And so finally, we can rewrite the partial derivative with respect to x as 5x to the fourth plus 6xy cubed. All right, and that's all there is to it. It's not meant to be too difficult. Partial with respect to y. Derivative of x to the fifth is 0. Think of x like pi or 5 or whatever number you want. I'm going to drop down the x square because it's going to be a constant. And then the derivative of 3y cubed is going to be 9y squared. And then finally the derivative of y to the fourth is going to be 4y cubed. And the 0 just goes away. 9x squared y squared plus 4y cubed. Those are your partials. Not meant to be difficult by any stretch of the imagination. A second example where we start utilizing some of the rules of derivatives that we've seen in Calculus 1. Now, a trick you probably remember from Calculus 1 is to take the derivative of any sort of radical expression. First, what you have to do is you have to rewrite it so that you have the 1/2 power, all right, or whatever the index is, in this case just 1/2. And now what we're going to do is we're going to find the partial. So f sub x is going to be equal to 1/2 x squared minus y squared. We're going to subtract 1 from 1/2. But now what we have to do is we have to remember that there's a chain rule of derivatives. So we're going to have to take the derivative of the interior function with respect to x. So that means we're going to multiply that by the derivative of x squared, 2x. The derivative of y squared with respect to x is 0. And if we just put this back together, we know that the 2 and the 1/2 are opposites, or I'm sorry, inverses of one another. They're going to cancel. And another way to write this is negative x divided by the square root of x squared minus y squared. All right, just by rewriting it back into the form, taking the negative 1/2, moving it to the denominator, etc. Fy. We're going to get almost the exact same derivative. So 1/2 x squared minus y squared to the minus 1/2. And then we're going to multiply that by the derivative of the interior function, all right, which is going to be negative 2y. And I must apologize. Up here, I think that I thought that this was a negative symbol. All right, so I do apologize. It should be positive for the x up there. Okay, so sorry about that. And then finally, we're going to simplify this. 1/2 and 2 cancel out. And then negative y over square root x squared minus y squared. And that's going to be our partial with respect to y. All right, so just a couple more examples. These are a little bit tougher because they have a little bit more going on with the interior functions. So we have our partial of x. Derivative of e is e, so we have e to the xy. And then the derivative of xy with respect to x is going to be 1y, or just y. Derivative of cosine is going to be a negative sign, so we have negative negative, which makes a positive sign. We're going to keep the interior function the same, and then the derivative of x squared y squared with respect to x is 2xy squared. Finally, derivative of arcsine, remember that's 1 over the square root of 1 minus whatever's inside of that function, squared. All right, so that's x cubed, y cubed. But then we have to multiply it by the derivative of the interior function with respect to x. So it's going to be 3x squared, y cubed. All right. Now, when we take the derivative with respect to y, we're going to notice that it's almost the exact same thing, except we're probably going to be replacing a lot of the x's and y's, interchanging them. So, fy, derivative of e is e to whatever. The derivative of xy with respect to y is going to be x. Derivative of negative cosine is going to be positive sine. So we have sine x squared y squared. The derivative of x squared y squared with respect to y, 2x squared y. Finally, derivative of arcsine is still 1 over the square root of 1 minus x cubed y cubed square. And then we take the derivative of the interior function with respect to y, so that's going to be 3x cubed y squared. Alright, so again, notice that these two functions' derivatives look very, very similar to one another. The only difference is most of the time we just interchange the x's and y's on their derivatives. So you can start getting the patterns down with that. One final example. X squared ln x sine xy, and we want to find the derivative with respect to x and with respect to y. Right. Now, with respect to x is actually a little bit more difficult because what you'll notice is we have two different functions of x going on here, which means that we have to use the product rule. Remember, product rule f prime g plus fg prime. Okay, so go back to Calc 1, remember your product rule. And so f sub x is going to be derivative of x squared is 2x, so that's your f prime. And then the other function just comes over, ln x plus sine xy. And then plus x squared stays where it is. The derivative of ln is 1 over whatever's inside the parentheses. So that's 1 over x sine xy. But then we also have to multiply that by the derivative of that interior function. So we're going to say times derivative of x is 1. Derivative of sine xy is going to be cos xy. But then there's also a chain rule inside the cosine. All right, so derivative of xy with respect to x, that's going to be a y. All right, so I'm going to clean this up a little bit so we can get a final product. And so f sub x is going to be 2x ln x plus sine xy plus x squared quantity 1 plus y cos xy, and then we're going to divide all of that by the x plus sine xy. Alright, so a pretty tough one. Alright, lots of chain rules going on there, product rule. Alright, so just be careful when you're doing these. Fy is much easier. Okay, so for Fy, the x squared is just basically going to be a 5, so that's just going to come down. The derivative of ln, now this is sneaky, but because there's a y inside of there, it really is a function of y. So x squared gets copied down. The derivative of ln is 1 over whatever's in the parentheses, so in this case x plus sine xy. Now we're going to multiply by the derivative of what's inside of those parentheses, but with respect to y. So the derivative of x is 0. The derivative of sine is cosine. But then we have to take the derivative with respect to y of the interior xy. Derivative of xy with respect to y is just going to be 1x. Right. And so finally, if we wanted to put this into a really nice form, all right, just to write it out, we can go ahead and we're going to write this. So we'll just say this is going to be equal to x squared, x cubed actually, because we have x squared and then x, and this 0 doesn't matter. So we end up with x cubed cos xy. And then we're going to divide that by x plus sine xy. So it actually doesn't look too bad after we're done. Just being able to get to Fy is pretty challenging. Alright, so hopefully this gives you a good overview as to how to find the first partials of a number of different functions. In the next video, we're going to take a look at how to find the second partials.